We are going to study about quantum mechanical model of the atom. But before delving deep into this model, we need to understand what is quantum mechanics and how is it different from classical mechanics. Okay, so classical mechanics is the mechanics of macroscopic objects, big objects, not of microscopic scale. Whereas the quantum mechanics is the mechanics of microscopic objects like atoms or the objects which are smaller than atom. In classical mechanics, we study the behavior, the nature, the movement of these macroscopic objects. Whereas in these quantum mechanics, we study the same things about the atoms, about the objects which are smaller than atoms like electrons, protons, neutrons. Classical mechanics is very much deterministic. I mean, if you will look at the object, you can determine where is it going, after how much time, where it will be, or you can easily predict its future. Like for example, you can see in this image that the batter has struck the ball, and this ball has come here. Now the catcher stands at that very position just by looking at the ball, judging its velocity. At the same time, it judges the forces also. Even if this person doesn't know anything about physics, then also he stands at that very position because he can predict the future looking the trajectory of this ball at the position where he could be able to catch the ball. So future of this macroscopic object is predictable by just looking at the trajectory, velocity and the position of the ball. But in the case of quantum mechanics, it is not possible. The objects are so small, so very small, that they're looking at them just cannot precisely you can determine what will be the path, what will be the trajectory, where it is going to in the next few seconds, where are you going to see that atom, that electron or proton or whatever it is. So here we don't know exact location or exact position or exact momentum at the very same time. But we talk here, in this case, in the case of quantum mechanics, we talk about the probability, where is the probability, where is the most where the electron is most likely to be present. We don't talk about the precise position, but we talk about the probabilities in quantum mechanics. Now we will talk about the quantum mechanical model of the atom. Before understanding it, we need to know what two things lead to it. Okay, so there were two developments which were made. One was the dual behavior of matter, and other was the Heisenberg uncertainty principle, which actually laid path for quantum mechanical model of the atom. So we'll understand first the dual behavior of matter, and then we'll understand the Heisenberg uncertainty principle, and then we'll come to quantum mechanical model. So what actually is dual behavior of matter? What is dual behavior? See, there are two types of things around us. Either it is energy or it is matter. Energy is in the form of waves. It is in the form of waves, and matter is in the form of particles. Okay, which has certain mass. And these waves have no mass, like light energy. You can take an example as light energy. Okay, it travels in the form of waves and it has no mass. Whereas matter around us is in the form of particles, and it is discontinuous. Energy is continuous in nature, and matter is discontinuous in the form of particles. It is discontinuous and it has certain mass. So these are the two behaviors, the wave nature or wave behavior, or the particle nature or the particle behavior of the things around us. Light was thought of as showing a wave nature. So it was thought that earlier that if anything is showing a wave nature, it cannot be particle like, or if it is showing a particle nature, it cannot be wave like. So light was thought of showing a wave nature, but later on there were certain effects or phenomenon that were shown by light that cannot be explained if we consider light only as wave. So these phenomenon actually indicated towards the particle nature of light as well. This is where the dual behavior of light first came into existence. And Max Planck was the first person to say that light does not only exist as wave, but it behaves as particles, in the form of particles also. So light shows dual behavior. It exists in the form of waves and also in the form of particles. Now, for anything to show to be wave-like, it should give interference pattern when passed through double slit. So it was seen that when light is passed through double slit, it showed this interference pattern. That proves that light has a wave nature. Then how it shows a particle nature? For particle nature, it was seen that the photoelectric effect was observed. Photoelectric effect cannot be explained if we do not consider light to be in the form of particles. Okay, so what is exactly photoelectric effect? We will learn about it now. It was observed that when light is shown on a metal surface, the metal surface has metal atoms, which has electrons binded to the nucleus with certain binding energy. This is B, binding energy. With certain binding energy, they are binded to the nucleus. When this light falls on this metal surface, the energy of this light is absorbed by the electron. Okay, so if the energy of the light is h nu, where nu is the frequency of the wave, light is in the form of wave, so nu is this frequency of the wave. So this wave, this light actually has energy h nu. If this h nu, the energy of the wave, is equal to the binding energy of these electrons, okay, is equal to the binding energy of these electrons, uh, then these electrons will be free from the nuclear attraction, okay, and they will be free, they will move about freely in the metal. But when h nu is more than binding energy, when h nu is more than binding energy, then the extra energy will be imparted to the electron as kinetic energy, okay? So the free electrons will leave the metal surface with this kinetic energy. And this is what photoelectric effect is. So this effect is actually used in our solar panels, where electricity is generated by the use of solar energy. When solar energy falls on those panels which have metals, the electrons get ejected and electricity is produced. Now here you can see this is a visible range of light. Okay, so there are different colors in this visible range and their energies. The violet energy, the blue light's energy, the cyan, the green, the yellow, and all these energies are given. Here in this table you can see the metals and their binding energies. Okay, so the cesium metal electron is binded with this much energy, the potential electron is binded with this much energy. So if we want to remove the electron from, say, calcium, okay, so it has a binding energy of 3.2. So we need light which has energy which is greater than 3.2 electron volt. Here we can only see the violet light which has energy of around 3.26 electron volt. So this light will be useful to eject electron from the calcium. For lithium, we can say that we can manage with blue light. It has energy which is in the range of the binding energy of the lithium. So now you can be sure of by seeing these two tables that which energy, which light energy should be used, or which light should be used to eject electrons from these metals. But classical electromagnetic theory was of different view. Okay, what classical electromagnetic theory said that only the amplitude or the intensity of the light affects the emission of electrons, not the wavelength. Okay, so it says that energy of the light is not useful in emitting the electron, but the intensity of the light is. So if you want to eject electrons from, say, lithium, which has a binding energy of 2.5 electron volt, you can use any of these lights. Even the lights which have lower energy than the lithium's binding energy, you can use that light also to eject electron from lithium. But what you have to do, then you have to use an intense beam, okay, the strong beam to eject electron. And if you use a dim light, then the electrons will get ejected, but at after some time. Here in this figure you can see a metal surface which has a binding energy of 2.5 electron volt, and the light which is used is of lower energy, that is 1.98 electron volt. So what classical electromagnetic theory said, that for any metal surface with any binding energy, you can use any light, of higher energy or lower energy than binding energy. But if you are using a low energy light, then you have to use an intense beam or more light to eject the electrons, and the electrons will get ejected instantaneously. But if you are using the same very metal surface and the same very light, and you are using a dim light or a very less intense, low intense beam, then you have to wait for few minutes in order to see your electrons getting ejected. So, classical electromagnetic theory believes that light is in the form of waves, and waves are continuous. So, there is a continuous transmission of energy to the metal surface. Okay, so even if you are using then a light of lower energy than the binding energy of the metal surface, and you are using a dim light, also a very less intense light, then the electron will absorb this light. Okay, and since the light is in the form of wave, and there is a continuous transmission of energy, because waves are continuous in nature, there is a continuous transmission of energy, the electron's energy will slowly increase. 1.98, then 1.99, then 2.0, and slowly it will reach 2.5 electron volt, which is the binding energy of the metal atoms, which is the binding energy of the electrons. So ultimately the electrons will get ejected after a few minutes after a few minutes. So the dim light needs few minutes to eject the electrons. Whereas when the intense intense light is used, then the electrons are ejected instantaneously. This is because too many beams now are striking a single electron, so its energy increases very quickly to 2.5 electron volt, and therefore the electron gets ejected instantaneously. So, according to classical electromagnetic theory, only the intensity of the light is important, not the energy of the light. High intense beam will eject electron instantaneously from any metal surface, whereas a low intense beam will take few minutes to eject the electrons from any surface, even if the light is of low energy. Then also,